This is part 2 of the two-part series on ETAP's Microgrid Controller solution. Part 1 focused on Microgrid Controller definitions, their purpose, and on how ETAP Microgrid addresses some of the pain points of using conventional controller. Part 2 focuses on ETAP's Microgrid Controller hardware and on how to test and validate the controller logic, and finally on how to monitor the Microgrid Controller before and after deployment. ETAP Microgrid covers a wide range of applications, from commercial and industrial power systems to residential communities and military bases alike. Either inland or offshore, domestically here in the US or abroad, in all cases meeting local practices and guidelines. Although our solution covers a broad range of applications, the exact microgrid controller strategy and associated control function still depends on the type of microgrid and its assets, ratings and sizes, operation conventions, and reliability requirements. One approach to implement microgrid controllers is to produce a generic controller. This approach offers flexibility to achieve desired control functionalities, although practically it may be limited to a certain level of control. In addition, this approach requires an engineering effort to develop and test the control functions for each microgrid project. Therefore, generic microgrid controllers may be limited to level 2 control and may not be suitable to implement for level 3 functions such as economic dispatch. Another approach is to develop a generic microgrid controller with predefined functionalities. In this approach, the types of resources, constraints, and overall objectives are part of the predefined functionalities. The main drawback of this approach is that any new requirement of functionality that is not supported by the existing control functions may not be achievable without an additional product development. ETAP's Microgrid Controller solution allows both approaches. That is, users can program controllers either from scratch or by using the built-in controller functions that come with ETAP. In either case, users work with the digital twin of the microgrid controller hardware. A digital twin is a virtual microgrid controller that appears on the ETAP schematic as any other element. This means that you can click it, drag it around, and configure it many times until it produces an adequate response for the electrical network under study. A byproduct of using digital twins and advanced monitoring is reduced risk. This means that all design and testing can be done without involving hardware. Then, an additional layer of validation is possible when the hardware is involved. That is, when we deploy a digital twin to the hardware, we get one step closer to field conditions. This constitutes an added layer of validation. This last layer allows tuning the controller against real-time simulators immediately before commissioning the controller at a site. One thing that should be pointed out is the hot swap feature. Once the controller is deployed into a hardware, it can be hot swapped or replaced by another without further wait times. This feature is incredibly useful for fine-tuning. We have an ETAP machine, which is where users start from. ETAP contains and runs the power system model for which the controller is being designed for. On that machine, users have access to a multitude of tools, including a control system designer, visualization capabilities, and analysis features. This is the starting point to working with ETAP Microgrid. This machine is where the digital twin resides and what you interact with before deploying it to the hardware. When a user is satisfied with the response of the digital twin, users deploy that controller logic into the ETAP Microgrid controller hardware. That hardware contains a data server and a runtime for the controller logic. Once the controller logic is deployed, the data server handles all communication in and out of the hardware. The controller runtime executes the controller logic that was deployed from the digital twin. In other words, the data server communicates with field devices, ETAP, and monitoring tools, whereas the controller runtime only executes the controller logic. So this would be one possible example where data is already being collected from an offshore site and being monitored with ETAP real-time. To add ETAP's Microgrid Controller solution to this scenario, we would install a validated controller, communicate with the site slaves, and start issuing control commands to them. This retrofits ETAP Microgrid to an existing site while keeping the existing communication infrastructure. Additionally, the microgrid controller can call any existing ETAP machine for added intelligence. For example, the microgrid controller can ask ETAP to produce a study or run an optimization query. These results come back to the controller for more intelligent responses. Now we'll talk about validation. How do we validate the controller logic? Well, we don't have to do much. In the design stage, users already tune the controller to the microgrid model. After the design stage comes the testing stage, which is the second row in this image. In the testing stage, we deploy both the electrical model and the controller model to separate hardware. The ETAP model typically goes to a dedicated real-time simulator. The controller model goes to the microgrid controller hardware. Then, these two independent pieces of hardware communicate over supported protocols in a controller hardware-in-the-loop arrangement. Finally, after the testing stage comes the commissioning stage. At this point, it is assumed that the microgrid controller is in tune with the intended network, validated, and is ready for commissioning. We do offer a direct way to export ETAP projects to OpenRT hardware. The OpenRT engine that is compatible with ETAP is ePhaser Sim. ETAP calls this export solution DRT Sim, and it is available upon request. Now, if you don't have a real-time simulator for the ETAP model, you can use ETAP Time Domain Load Flow as a real-time simulator. We leave it up to the users how to best test the electrical side. Let's show what we mean. Here we have the microgrid model shown in part 1 of this series. After we design the controller and test it inside of ETAP, it becomes time to deploy it to the hardware. So we double-click the controller element on the ETAP project schematic. This is the digital twin you've been working with all along. And we find the deploy button. A deploy tool comes up where you can confirm there is access to the hardware and ensure the settings are correct. You have several navigation panes that relate to how the deployment is performed. When you are ready configuring this tool, we click the deploy button. The tool will ask you if you want to test the controller before deployment. Typically we say yes. And finally, we get a confirmation that the logic was deployed to the hardware. At this point, the controller is running in the hardware. The controller can run at real-time speeds or even faster than real-time for those long-running scenarios. In this video, we don't have a real-time simulator. So what we use is ETAP's Time Domain Load Flow engine as a real-time simulator instead. This saves you from having to export the project onto a separate device. So what we see here is the microgrid controller running inside of the hardware and ETAP running its Time Domain Load Flow as a real-time simulator. In general terms, all of our boxes meet the same specifications. We offer rugged machines with shock protection, fanless enclosures, and support temperatures from -25 to 70 C. In all cases, we offer remote upgrades and significant storage without compromising size. Currently, we offer 3 hardware configurations. The form factor typically varies by size, weight, and computational requirements rather than cost. Starting from the left, we have a configuration which is lightweight and portable but has less computational power. In the middle, we have the most common configuration, which is rack mountable and fits most computational requirements. On the right, we have the high-end model, which comes with a server-type processor to better handle concurrent loads. The operating systems for hardware can be either Windows or Linux. If Windows, we support Windows Server and Windows 10. If Linux, we support Ubuntu and Red Hat distributions. The choice of operating system is typically dictated by cybersecurity concerns, OS preference, determinism, or simply by rule of thumb. ETAP's microgrid controller is also ready for co-simulation environments. That is, if you are already doing co-simulation between ETAP, electromagnetic transient tools, and even process control tools, then you could just join in the microgrid controller along with the mix. ETAP CoSim supports various ETAP engines and third-party tools alike, by exposing a generic and simple API for tools to plug into. ETAP CoSim orchestrates a co-simulation between all participants. Similar to the microgrid controller's data server, ETAP CoSim exposes data to ETAP real-time monitoring tools as well.
Now let's discuss the implementation of a microgrid controller. The microgrid controller will act as a master secondary controller to the energy sources in the microgrid system. It must be able to communicate to diesel generator controllers, battery management systems, photovoltaic inverters, and wind turbine controllers. For dispatch purposes, this might be sufficient. However, to get a complete picture of the microgrid assets, one must collect data from protected devices such as relays as well as power quality meters. The challenge becomes having the capability to communicate to all different types of controllers and devices. Many primary controllers in the market support proprietary protocols designed to communicate to the same brand of device. Communication between the same brand of device is relatively simple to configure, but it ties you down to the limitations of the functionality presented. As the manufacturers of different sources provide you with their own primary controllers, implementing a controller with limited communication options make it close to impossible to implement. Other option is deploying generic controllers that are programmable. They provide flexibility of functionality if you have the time to program, validate and test, in addition to the budget to invest in expensive tools for such testing. ETAP has kept interoperability into account when developing its microgrid control technology. The controller directly provides different protocols over Ethernet IP. In addition, it provides hardware extensions for serial protocols over RS-485 and RS-232. Let's not forget that when not implementing technologies such as IEC 61850, one must provide hardwire to open and close breakers, for example. In some cases, when necessary, the hardware extensions can be utilized to control diesel generators directly as well. The default communication protocols in the ETAP Microgrid Controller include DMP3 and Modbus TCP and IEC 61850 MMS. The computational response does not vary by the protocol. It varies by the logic. Its latency is around 1 to 10 milliseconds, while the communication is between 50 to 500 milliseconds response. This makes the controller very fast to address the functionality required from it. The ETAP Microgrid Controller extensions support at minimum the following protocols: IEC 60870-5, DMP3, Serial and TCP, Profibus DP, IEC 61850 CUS, Modbus RTU and TCP, and SNMP. ETAP can also provide protocol extensions for IoT devices such as LoRa 1 over MQTT and other protocols over 4G and more. The configuration of the communication system performed in a single application named the ETAP SCADA Integrator. The SCADA Integrator provides a library of communication settings for different brands and models to which the controller will communicate to. Here under Device Models, I can create a new device model, select what kind of device we're going to communicate to. We select the brand, the communication protocol, and we just assign a name. And now we can see all the different variables listed in the SCADA integrator. In addition, the alarm management settings and configurations are performed here. I can create an unlimited number of groups of alarms where I can go in any of the variables for this controller or device edit its alarm states. Define actions to which we want the controller to take actions on or to report on whenever a condition happens. So for example, I'm going to select just enter a high value. I can select different colors and put in an exit delay on the alarm. By selecting or setting up these alarm settings, they will be automatically be used by the ETAP alarm management system for this particular component. ETAP provides a communication of unlimited number of tags limited only by the hardware specs. As discussed, ETAP provides different form factors of the controller to handle small to large applications. In summary, the ETAP SCADA integrator provides you with an integrated library of communication settings, multiple protocols configuration, alarm management configuration, unlimited number of signals, and one common configuration for all the controllers. In a small implementation, the typical architecture will look like this, where a single microgrid controller will communicate to the sources and load device controllers using IP communications. The proper selection of primary controllers is important to limit required medium conversions to serial to Ethernet, for example. A single ETAP communication extension will be required for hardwiring the control signals to circuit breakers. In a large scale, the communication extensions can be used as data concentrators. In different parts of the system for communication to serial devices and hardwire control locally at each location in the microgrid. The extensions communicate to a single controller via Ethernet IP for overall system dispatch and management. The system is also designed to communicate to the system operators and distributed energy resource management systems such as ETAP Advanced Distribution Management Solution. Largely, the communication protocols utilized to communicate to the control centers include DMP3, IEC104, and ICCP. Now let's look at the tools provided by ETAP integrated in the controller system. Integrated in the controller is a web server that will serve the data to a customizable human-machine interface. As we can see, we can monitor all signals collected in the controller, such as wind turbine generation, PV generation, battery operating values, state of charge, loading values, and any other value that is available in the controller. This is only an example. ETAP will provide a template with a controller that can be expanded to monitor any information available. The human-machine interface also allows for trained objects, control buttons, alarm indicators, one-line diagram components, and many images as part of the library. The ETAP HMI designer will also be provided, which runs in a separate machine that can download the views to the controller. From this HMI, we can perform controls such as opening and closing a breaker, we can also access the microgrid controller settings and update any of them with the proper access levels. For example, I can go to the system information, which actually displays the devices that the microgrid controller is connected to, such as the energy storage device managers, the controller with a utility, and any other parameters such as execution rate, rated voltage at the connection point, normal frequency, and so on. Other parameters, depending on the functions that are enabled, include economic dispatch, where all the economic dispatch settings in the controller are actually displayed and can be actually customized here. Operating limits, frequency support settings, and any other setting available in the controller. Through this package, the operator dispatcher can study the health of each of the components in the microgrid system. For example, let's navigate to the wind generation page. In this page, we can appreciate the total generation from the wind sources. In addition, we can see the weather conditions such as wind speed, wind direction, temperature, barometric pressure, and more. Parameters that are directly related to the performance of the wind turbine. Through the trend window, we can appreciate how the system has been behaving for the last few hours. Remember, this is all customizable to the user and project. We can do the same for the solar network. Each PV panel group output can be monitored, the total combiner through output, as well as the total PV generation, and weather data can be monitored, which is important for understanding the reason of the solar performance. So for example, I'm recording this at night, so therefore we see 0 as the total generation from the PV system. Another important tool within the monitoring system is the trending view. The trending view allows me to see all different parameters available in the microgrid controller, and I can select any of them to actually be trended. In this case, for example, I'm trending the wind turbine generation current, real and reactive power measurements. You can do this in real time, as well as use user-defined parameters where you can select your from date to date and look at historical information. This all information can be exported to Excel for easier validation. Another important tool is the alarm manager. Through the alarm manager, the operator dispatcher can be notified of any abnormal condition, from the communication network to operation in the microgrid. In addition, alarms for maintenance can be built in for understanding when a component needs servicing. The configuration of the alarm system is performed at the ETAP SCADA integrator and downloaded to the controller. Notice the number of active alarms is displayed on the HMI. Click on the alarm icon to open the alarm manager. Active alarms flash on the screen. The operator dispatcher can acknowledge alarms by right-clicking on the alarm and selecting Acknowledge. The alarms will stop flashing as soon as they are acknowledged. Notification is very important. The system can be configured to email and SMS alarms to select a group of users and managers. One more important tool is the load and generation forecasting tool. The forecasting application utilizes the weather information, historical and forecasted, as well as the power historical data and current operating conditions to forecast generation and loading up to 1 month ahead in the case of short-term forecasting and years for long-term. The configuration is performed and variables for the forecasting can be configured. Here at the bottom we see the historical data utilized for the calculations, and at the right is the forecasted output. This information is utilized by the controller to perform decisions on the dispatch. One last tool that I want to show is the user-defined reports. These reports can be customized, scheduled, emailed, and generated on demand as the user sees fit. Here we can see on-demand reports generated on the spot. You can also have a scheduled reports. You choose the period and how often you want to get those reports into your inbox, or generated and accessed through the user report viewer from the web. There are other reports that are very important in addition to the historical and on-demand reports. is the alarm reason reports, which basically are tied to the events in the system. When alarm is generated, it can also provide you with a report indicating, the reasons for that alarm, which device took action and what other devices actually tripped during the condition. And there are also operator shift reports, which can be scheduled every 8 hours, or as the user defines, the shift, which will include operating values, alarms, and events that happen during the shift period. In this webinar, we'll learn about the ETAP Microgrid Controller implementation architecture and application. We looked at the ETAP Microgrid Controller utilizing the Digital Twin. We can also see the ETAP provides you with all the tools you need for testing environment with co-simulation, with important tools to evaluate the performance on the microgrid controller and the microgrid overall. We also address interoperability concerns, communication to utility operation centers and DERMS, such as ETAP ADMS system. And last, we took a look at the integrated monitoring tools for the operation of the microgrid. In other words, ETAP offers a complete solution for the design, testing, and operation of the microgrid. Thank you.